Hello students, welcome back. The next topic is eigenspace. What did we talk about? We talked about linear operators, a linear map from one vector space to itself, and then for the linear operators we can define eigenvectors and eigenvalues. L of v is equal to lambda v where lambda is not zero. Lambda can be zero where v is non-zero vector, then it is called an eigenvector. Lambda can be zero and that's eigenvalue. How to find out eigenvector? Set of linear equations. For example, checking straight up is too trivial. When an eigenvector is given, when an eigenvalue is given, then you can set up a system of linear equation to find out the eigenvector, kind of like these. Set it up and use elimination and substitution to find out, and plugging in typically some character equals to 1 to get an eigenvector. As long as you do not put 0, it's going to be okay. But why did anybody put in anything else? Because 1 is the second simplest. How to find out eigenvalues? It comes from characteristic equation, determinant of A minus Ti. How does it work? Well, Ti is T for all the principal diagonal, this 1, 1, 1, times all t's here and subtracting. So I have minus t, minus t, minus t. Everything else remains the same and take the determinant, set it equal to 0. That's a characteristic equation. Solve it and the values are characteristic values or eigenvalues. This is 4x4 case, a little bit harder, but the same deal, We have minus t, minus t, minus t, minus t. Everything else is the same. And then set this determinant equal to 0. That's a characteristic equation. Solve it and you get the characteristic values. Now that we have eigenvalues like those, you can find out eigenvectors. And you can consider vector space determined by those eigenvectors. Those are called eigenspaces. The set of all eigenvectors with respect to a specific eigenvalue lambda union with a zero vector forms a vector space, from the subspace. And that subspace is called an eigenspace. Now, unions with a zero vector, that's kind of strange, but it is necessary because according to our textbook author's convention, eigenvector cannot be a zero vector, but every subspace needs a zero vector, so we have to artificially take a union. Now, if you look at some other textbook, some textbook authors allow zero vector to be an eigenvector. In that case, this strange union part is not really necessary. It's kind of related partly to orthogonality, as a matter of fact. According to our textbook author, zero vector is orthogonal to every vector. Likewise, it is possible to define zero vector is an eigenvector for all possible eigenvalues. It is possible to do that, but our textbook author did not do it that way. So we need this union with zero vector to make it a subspace. The proof is left to the students. You have to check 3 things. Is zero vector in there? Well, that's simple because artificially we put it in. Now close under addition, close under scalar multiplication, or putting together, close under linear combination. You'll have to check those. Also, if you have m eigenvectors associated to a single eigenvalue lambda, then the set of all linear combinations, a1 lambda 1 plus a2 lambda 2 plus blah 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 all the way up to aml vm, the set of all linear combination form an eigenspace, formed a subspace, and that's going to be another expression of eigenspace if you found out all the eigenvectors. But the definition of eigenspace is actually part A. Set of all eigenvectors associated to one eigenvalue, union with zero vector. Let's consider an example here. let's see. We went through this already. And then what are the eigenvalues? First eigenvalue is 0. Second was 1. Third, 2. That was also 2. Do you remember this? It came from the previous problem. This one. And if you set up this characteristic equation and solve it, then you're going to get those. Now, let's find out eigenspace, and the easiest is this one. So let's find out. So what you need to do is to find out an eigenvector, and then get all the eigenvectors. But what you actually need is linear combination of those. Okay, anyway, let's go. Okay, this is equal to 0 times this. That's what we want, isn't it? Therefore, this is equivalent to all 0 vectors, where this one is, let's see, first row, negative 4x minus 2y plus 0z minus 2w. Next one, second row, this column, we're going to get 6x plus 4y plus 2w. And how about this one? Negative 6x minus 2y plus 1z minus 3w equal to 0. 6x plus 2y plus 0z plus 4w is equal to 0. That's what we get from this. Now, can you simplify this further before doing any elimination or anything? Let's do that. So let's simplify. Everything is even, so divide everything by 2. Oops. So that's negative 2, negative 1, negative 1. How about this? Divide by 2. 3, 2, and 1. This 2. 3, 1, 2. If I divide each by 2 and simplify. Okay, we had some simplification. And let's simplify this thing further. Okay, all right. I can add second row to the first row and eliminate W. Let's go ahead and do that. So add them up. 3 minus 2, so 1x. Add them up. 2 minus 1, so plus. And then minus minus cancel out. We have x plus y equal to 0. Now how about second row? The row looks like I can simplify. I can subtract. 3x, 3x, I'll cancel out. 2 minus 1, so that's just y. And 1 minus 2, so minus w. So by subtracting, you're going to get that. So looks like we are getting x plus y equal to 0, or y equals negative x from the first line. No, x equal to negative y, that's going to be a little bit better. Y minus w is equal to 0 from the last line. So w is equal to y. So I can plug in y here. So, alright, some elimination and substitution, that's basically it. So plug in negative y there, and then w is y there. So the first line and last line are trivial. Minus y plus y is also 0. Y minus y, that's 0, that's clear. And then how about the others? Plug in negative y here, and then w is equal to y. And then let's see, how about this? Minus y there, and then w is equal to y. Let's see. What further simplification do we have? And this one, 0. That one, 0 equal to 0. No big deal there. Minus 3y plus 2y plus y. So this is minus 3y plus 2y plus y equal to 0. So again, we'll get 0 equal to 0. So far, so good. And finally, I'm supposed to get something related to z here. Let's see. This is 6y, and then that's minus 2y. So that's 4y. Minus 3y. So y plus z is equal to 0. I hope my computation is correct. Z is equal to negative y. So x equal to negative y, z equals to negative y equals to y. So it looks like I'm getting this. Negative y, and then z is negative y, and w is y. Looks like this is the eigenvector. And if you're looking for one eigenvector, I can plug in y equals to 1 here. Because I need only one eigenvector, but if you want eigenspace, this is what you need. Or equivalently, you can write like this. Y times scalar multiplication out. 1, 1. So what do we have? We have one eigenvector and times y. So all the vectors parallel to this vector. So it's a one-dimensional subspace you got. Let's see if this computation is correct. Let me stop this recording a little bit here. And then, let's see, this is a computation. Let's stop this recording and then get some mathematical computation done. Give me a moment. Okay, I did my mathematical computation and it's here. Matrix A, we completed defining like this through each row. 4, negative 2, 0, negative 2, and then 6, 4, 0, 2, and so on. And then V0 is negative 1, 1, negative 1, 1. And that's for rows. So I want column vectors, so I took the transpose to make the column. And then I did this computation. AV minus 0V. And turns out 0. So yes, AV and 0V turned out to be the same. So all the computation is correct. I just checked it, and here are the computations. So eigenspace for lambda equal to 0, and that's for V0. How do I do that? Basically, I'm looking for an eigenvector by setting up a system of linear equations, elimination and some substitution, and then get what we want. And either you can express it as the set notation here, where y is arbitrary real number, or you can express it as a linear combination or scalar multiplication in this particular case, because there's nothing else to add. So from here you can see that this is one-dimensional subspace. A scalar times a vector, a non-zero vector. So all the vectors in this direction. Okay. And then the next one, oops, sorry about that, wrong cell. Next, what if you have lambda equals to 2? Okay, lambda equals to 2. That's going to be harder because you see, we did this one, the simplest case. This one probably almost equally is the same, except maybe a little bit more complicated because one is not really hard, so it's going to be about the same level. This is going to be harder, not because 2 is more complicated than 0 or 1, but because there's a duplicate. And we expect, as a matter of fact, two-dimensional subspace here. So that is the difficulty. So how do you do that? Well, okay. Oh, wow. Too complicated. Well, okay, in this video, let's just follow that, and then we'll do this again in a separate video. Okay, here we go. So, instead of x, y, z, w, I'm using x1, x2, x3, and x4. Okay. In any case, here you go. 2 times that. So we can put the left-hand side together, and we get this matrix computation. Right-hand side is 2 times all those. And then we can use appropriate elimination. Flip all the left-hand side to the other side, so we get 0, 0, 0, 0. And then conduct appropriate elimination. If you do it right, you can remove 2 rows like this. And then we get first row and the third row. We lost 2 informations out of total 4. So 2 left, 2 information gone. So 2 of those characters are running freely. So we have 2 dimension. Previously we lost only 1, so 1 dimension. So x3 and x4, x4 is negative of x3, and there's that relation. Maybe I want that previous one back. So that gives me from here, and from the other one, I can find out x4, and they're determined from x1 and x2. I decided to use x1 and x4. Either way, it's fine. I need 2 degrees of freedom, basically. And then I'm plugging in 1 and 0 and 0, 1, respectively. And we get 2 vectors. And then subspace generated by these 2 vectors, 2 eigenvectors, is the eigenspace. I did this really quickly. So in the next video, I'll do this all over again, very, very slowly. See you soon.